What if I told you that a simple covering property can determine whether a space behaves like a metric space? Today, we explore paracompactness and how it leads to one of the most important metrization results in topology. To understand this, we first need to look at how we measure a space using covers. This text defines an open covering, a collection of open sets whose union contains the entire space. If we pan down to the next definition, we see the criteria for a compact space. A space is compact if every open covering contains a finite subcollection that still covers the entire space. Mathematicians highly value compactness because it reduces infinite problems down to finite ones. If you can cover a space with a finite number of sets, calculations become manageable. The problem is, true compactness is incredibly rare in practice. Look at example 1 here. The real line cannot be covered by a finite number of open intervals. If you try, you will inevitably leave points exposed, stretching off to infinity. Since most essential mathematical spaces are not compact, topology requires a weaker, more flexible property. We need a property that allows for infinite covers, but still imposes strict structural discipline. The ultimate objective is metrizability. We want to determine if a topological space can be equipped with a valid global distance function, defined here as a metric d. Many topological spaces are locally metrizable. As this section on the epsilon ball shows, if you zoom in close enough to a specific point, the immediate neighborhood behaves perfectly like a standard metric space. To create a global metric, we have to stitch all of these localized metric neighborhoods together. But if an infinite number of these local metric neighborhoods overlap at a single point, the addition fails. Summing infinite local distances causes the calculation to blow up to infinity. The central challenge of metrization is finding a topological property that organizes these covers so they never pile up infinitely at any single location, allowing safe global stitching. To solve this overlap problem, we need a specific mathematical tool called a refinement. Consider an original open cover, represented by these white circles over a space X. An open refinement is a secondary cover where every set is contained within at least one original set. These new yellow subsets give a tighter, more granular fit, preserving the topology defined by the original cover. However, taking a refinement does not automatically eliminate the infinity problem. You can still have an infinite number of these refined sets overlapping at a single point. A refinement only gives us smaller, better-fitting pieces. We still must impose a strict mathematical rule on how those pieces are allowed to touch. That strict rule is called local finiteness. A covering is locally finite if every point has a neighborhood intersecting only a finite number of sets in that cover. Even though the overall space contains an infinite number of sets, from the perspective of any single point, it only ever sees a few. This brings us to the formal definition. A space is paracompact if every open cover has an open refinement that is locally finite and covers the space. Compactness demands the entire space be finite. Paracompactness accepts that the space globally is infinite, as long as it maintains strict local finiteness. Take the real line again. You can cover it with overlapping intervals like n-1 to n+1. That is an infinite cover globally, but any single point exists in a maximum of 2 intervals locally. By taming the infinite overlaps, paracompactness provides the exact mathematical discipline required to finally define a global metric. This leads directly to the ultimate payoff, the Smirnov Metrization theorem. The theorem states that a topological space is metrizable if and only if it is a paracompact Hausdorff space that is locally metrizable. The locally metrizable condition ensures the space has valid micrometrics. The Hausdorff condition ensures that distinct points can be mathematically separated from one another. The paracompact condition is what makes the calculation possible. It grants mathematicians access to a tool called a partition of unity. A partition of unity allows us to take all those isolated local metric equations and sum them together into a single global distance function. Because paracompactness guarantees local finiteness, this addition equation will only ever have a finite number of non-zero terms at any given point. The sum remains mathematically safe. The Smirnov theorem proves that paracompactness is the necessary condition to promote local geometric structure into a global distance metric. We can test the limits of this theorem by looking at pathological spaces where metrizability completely fails. This text outlines a classic counterexample, the infinite product space R omega in the box topology. Despite its ordered structure, the box topology lacks topological discipline. As the sequence formula at the bottom shows, it allows infinite sequences of points to fail to converge. Another conceptual pathology is the long line. The long line appears perfectly well behaved at first glance. It is Hausdorff and locally metrizable. If you zoom in, every small segment looks exactly like the normal real line. But the long line is formed by an uncountable concatenation of these lines. It is entirely too long to admit a locally finite refinement, meaning it is not paracompact. These counterexamples confirm that local geometric perfection cannot yield a global metric without overarching global discipline. For students preparing for advanced topology exams, this theorem provides a practical, logical framework. A. H. Stone's theorem states that every metric space is automatically paracompact. In a true-false scenario, if a question proposes a space that is metrizable but not paracompact, you can immediately rule it out as a mathematical impossibility. The implication chain is equally strict. A compact space is always paracompact, but a paracompact space is not necessarily compact. Just remember the infinite real line. Paracompactness tames the infinite overlaps. Locally finite refinements are the geometric mechanism that makes it possible, and the Smirnov Metrization theorem stitches it all together. If you found this explanation helpful, don't forget to like the video and subscribe for more book-based mathematics explanations.